up until now, we've been talking about liquids. So let's spend just a few minutes talking about solids. This is very complex stuff and really goes beyond honors chemistry. If you become a chemistry major, you'll find there's several classes that deal with this stuff. But I'm just going to touch upon this. There are 4 kinds of crystalline solids. Now you only see 3 up here, but there's a 4th kind that I'll show you. Okay, ionic solids, of course, are metal, non-metal. Molecular solids would be non-metal, non-metal. Atomic solids, I'm going to split into 2. Non-metal solids and metal solids. Non-metal solids and metal solids. Okay? Which one is this? Well, what is it? It's graphite. It's made up of just one carbon. Is it non-metal, non-metal? No, because it's not 2 different non-metals. Is it metal, non-metal? No, because it's not 2. It's only one type of atom. So it's either going to be metallic or atomic. Is carbon a metal? No. So it's atomic. How about this? Sodium chloride. Is it metal, non-metal?
Yes.
Yes. So it's ionic. How about this? Hydrogen and 2 oxygens. That's water. Is it metal, non-metal? No. Is it non-metal, non-metal? Yes. So it's molecular. And I don't have an example of this, but if it was 2 metals, it would be metallic. So ionic would be sodium chloride, ammonium nitrate. Molecular would be CO2, H2O. Atomic would be carbon. Let's not call that atomic. Let's call that metallic. Would be iron, and atomic would be argon. What are the characteristics of ionic solids? High melting point. These are the strongest bonded materials. They will have some of the highest melting points. They are held together by very powerful electrostatic forces. The patterns that they form are called crystal lattice or crystal lattices. Crystal lattice. The interesting thing is when we say NaCl, we're actually kind of simplifying it. Because for every Na you have 1, 2, 3, 4, 5, 6 chlorines surrounding you. So why isn't it NaCl6? Anybody? Yes?
That's for every chlorine, you also have 6.
1, 2, 3, 4, 5, and you can't see that, but there's 1 behind it, 6. Yeah. Yeah, so when we're talking about ionic compounds, we're talking about so many things that it's best just to make it the lowest whole number ratio. They form these crystal lattices which create all these beautiful designs, or a lack of design. That looks like it's not a design, but actually if you look at it under the microscope, you'll see its design. There's a whole branch of chemistry dealing with this stuff. What are the characteristics of molecular solids? Low melting point. Covalent bonds are weaker than ionic bonds. They're held together by intermolecular bonds like dipple and London dispersion forces, it's nothing compared to ionics. Nothing compared to ionics. Very weak bonds, low melting point. Atomic solids. Why does melting point decrease as you go down a period from carbon, nitrogen, oxygen, and fluorine? It has something to do with the way they bond. Carbon can bond 4 times, so that makes it a stronger bond. Nitrogen will bond 3 times to itself. Weaker, but still stronger than oxygen, which bonds 2 times to itself. And finally, fluorine bonds only 1 time. So the number of bonds to itself actually gives you strength. Wow, my computer's going absolutely nuts. Why is diamond considered to be a giant molecule? Each carbon has formed single bonds with 4 neighboring carbons, and it goes on like that. Those are examples of allotropes. Allotropes are different forms of the same element. Some of you guys are writing with a pencil. You're writing with graphite. You go, no, that's lead. No, maybe it was lead back several hundreds of years ago. Now it's graphite mixed with clay. Graphite is the same thing as diamonds, just arranged differently. 2 major types of oxygens. There's the oxygen that we breathe, and then there's ozone that you don't want to breathe. Ozone is very corrosive. 2 types of sulfur, S4 and S8. This is S8. S4 is gummy. It's orange and gummy. Looks like something R2-D2 would drop off when it went to the bathroom, doesn't it? So this right here is LDF, holding those molecules together. Okay, metallic bonds. What are some characteristics of metallic bonds? Strong, malleable, ductile, conducts heat and electricity. And there's one explanation for all of this. That explanation is called the sea of electrons. The sea of electrons. Back in the 1960s, there were these things called communes. That's where everyone would come together and everyone would share, like a little bit of Marxist communism in a little community. It didn't work. They all became the capitalists of the 1980s. But everyone shared the responsibilities of even raising their own kids. So if you didn't want to sleep with your parents, you'd go and sleep next door with your best friend's parents. Okay, I kind of think of metals as being these communes. The sea of electrons are the outer shell electrons that don't stick with the atom that they originated from. They kind of just take off and they flow around. It's called the sea of electrons. No one actually owns those outer shell electrons anymore. Yes?
So that's only with
metals. Yeah. Only with metals. No one owns those electrons anymore. They're free to move around. The sea of electrons. How does C explain conductivity of heat and electricity? Well, in order for electricity to move, you've got to have movable negative or positive things. Are there movable negative things in the metal? Yes, the sea of electrons. In order for heat to move, it must be carried from one side to the other. Are there movable particles in a piece of metal? Yes, the sea of electrons.
When aluminium atoms come in contact with each other, the outer shells overlap, and this allows the outer electrons to escape from the individual atom. they become delocalized, moving at random to form a sea of electrons between the atoms. This has dramatic effects. The atoms become positive ions, sometimes called cations, because they now have more protons than electrons. They are strongly attracted to the negatively charged sea of outer shell electrons enveloping them. This attraction is the glue that holds the particles together. Because all the ions are the same, they pack up into a regular lattice arrangement. And because they have effectively lost their outer electrons and have filled outer shells, they are now much more stable than they were as separate atoms. This model basically applies to all metals and explains why they are such good conductors of electricity. Normally, the delocalized electrons move at random through the lattice. There's no net movement one way or the other. But if a positive charge is applied to one point of the metal and a negative charge to another, the delocalized electrons will tend to move towards the positive charge. This is what an electric current is, a flow of electrons.
Here's another way of looking
Though
at it.
metal atoms group together in a crystalline lattice structure, they have very different properties to the ionic solids. For example, solid metals are able to conduct electricity. This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom. Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations. The structure is held together by the strong electrostatic force between the sea of valence electrons and the metal cations. This is called metallic bonding. The electrons are constantly on the move, so the bonding acts in all directions. Metallic bonding is powerful enough to overcome the force of repulsion between the closely packed cations.
Okay. How does the sea of electron help explain? Yes?
Why, if there's already those electrons in that outer shell different, do they use electromagnets? Like, why do they have to run electricity for it if there's already those electrons?
Okay, you're talking about things that are not normally, don't normally have the sea of electrons. They can be made to have a sea by running electricity through it. Electrons act sort of like saran wrap to keep the metal atoms from fragmenting. Ever put saran wrap around my mom used to saran wrap my sandwich. And then I discovered that you could sit on the sandwich and it would flatten out, but it'd still be a sandwich. So I'd get it out and be like a pancake. Okay? Why? What prevented it from fragmenting? The saran wrap. Think of the sea of electrons as being kind of like saran wrap, holding the shape. The ability to form mixtures with other metals can also be explained by the sea of electrons. What do we call this? Alloys. Alloys. Two kinds of alloys. Substitutionary, where the host metal is replaced by other metals of similar size. Brass and copper. Sterling silver is a good example of an alloy. Pewter, and I love that word, pewter. Pewter. Okay, so this is substitutionary, where you get atoms of similar size to join in. This is called interstitial. This is where you put small atoms in between the cracks. This is steel. That's steel. Interstitial is where some of the smaller atoms fit into the holes. That makes all the different kinds of steel. It sounds like it's almost describing salsa, doesn't it? You know, mild, medium, hot.
Oh.
So you can actually have a mixture. So these are alloys, and this is all I wanted to teach you about solids.